Hi everybody. Really quickly here, we're going to look at if we have unknown values plugged inside our matrix, and we are told to find these values to make the whole matrix uninvertible. So we're going to go through a quick example for that. Hopefully it's. And so what you see on the screen is our example. What values of sigma, if any, will make the following matrix singular. So remember that a singular matrix is a matrix that is not invertible. So that's what singular means if it pops up, okay? So non-invertible matrix is a singular matrix. So its inverse does not exist. So a bunch of ways to say that. So let's jump into this. So the strategy for these, let's spread it out. So we are going to take the inverse. Actually, we're gonna no, wait, we're going to take the determinant. We're going to take the determinant, and then we know that any matrix that is not invertible, the determinant will equal 0. So that's why we're going to set the determinant to be equal to 0. We're going to call this matrix A. And then we're going to use this equation to solve for all values of our variable. So let's jump right into taking the determinant. So once again, we are going to use cofactor expansion. We are going to pick the line with the most zeros in it, and we are going to multiply each number in this column by the cofactor for that spot. So obviously we have 3 zeros, which is going to reduce the work we have to do. So we're going to, so the determinant of matrix A is going to be equal to this number, each number, and obviously the rest of them are zeros, so it's going to be this number times the cofactor for that spot. So this is row 4, column 4. The cofactor of row 4, column 4 evaluates to -1 raised to 4 plus 4 times the minor at row 4, column 4. So this cancels out as just a multiplication by 1 because that's an even exponent, as 4 plus 4 is 8. 8 is even, so there will be no change of sign. So now we're going to find the minor at row 4, column 4. So we're going to keep our multiplication there. Messed up the 7. So it's going to be the determinant of everything else once we've ignored all the numbers that share a row or a column with our the number we chose. Not the number we chose, the number we are currently cofactoring. So we're going to ignore everything that's highlighted and take the determinant of the rest. So that gives us the determinant of 1 sigma 0, 2 1 negative 2 0 sigma sigma, and then now we can pick any row or column that has 0 in it, or any row at all. But we're gonna go. Let's go with our first row here. So this will give us so we're going to keep this out in front, and then we are going to cofactor for each term in this row. So we're going to have 1 times the cofactor at row 1, column 1. Oops, sorry. This will evaluate to -1 times 1 plus 1 times the minor at 1, 1. This will cancel and will give us simply 1 times the minor at 1, 1. And we're going to add the second element times the cofactor at that spot, which will give us -1. So it is in row 1, column 2. And we're going to multiply it by the minor at this spot. So be that. Practically didn't have to be that big. So obviously we have 7 minus our variable, minor at 1, 1, minus our variable times minor at 1, 2. So let's have a look at our minors here. I didn't name these, but that's interesting name. So let's look at our first one. We are going to ignore everything that shares a row or column with our number up here. So this will give us to lead us to take the determinant of what's left. So if we have a look, and we're going to take the determinant of, let's write this. So we're going to take the determinant of 1 minus 2 in our variables. We're going to minus variable times the minor. So make sure that you pick the different spot. So this time we are ignoring this column. So now we're going to take the determinant of what's left here without the stuff crossed there, okay? So this will give us, oh, oops. Anyway, so this will give us 2, -2, 0 in our variable. Oh, it would have been helpful if I wrote it in pen. So that gives us, all right, so obviously it's good that we started with a 4x4 matrix, otherwise we'd be going through cofactor forever. But now we have our algorithm for the determinant of a 2x2 matrix we can go by relatively quickly at this point. So let's see. So we have we have this number times this number minus this number times this number, and we're gonna do that twice. So if we so we have those numbers minus that number minus the determinant of this times the determinant. We have 2 of our variable plus 2 times 0, which will be which I won't be writing here. So this gives us, we're going to go through a few steps here. Sorry. We have an addition here with our double sign. So we collect like terms, we will have 3 of our variable minus 2 of our variable squared. So I'm not going to expand this and do FOIL or whatever you call it. So we've taken our determinant, we're going to set it equal to 0. So that's leaving it in factored form will help us find our the values of k, or the values of our variable sigma, that will satisfy the requirement of having a singular matrix. So for singular matrix A, the determinant A equals 0. So set it equal to 0, so this will be equal to 0. So now each factor, there should be, all right, so now we can, there should be an extra factor somewhere. I'll have a look at that in a bit. All right, so yes, there is a common factor. We are going to, we're gonna delay a step here. We're gonna common factor our variable out of both terms in the second set of brackets. So that leaves us with 3 minus 2 of a variable. So now we can apply our zero product property that we are probably really familiar with by now. Sorry. So obviously any one of these terms can equal 0, and that would make the whole thing equal 0. That's how this works. You've probably done it a million times before. So we can declare that one solution is sigma equals 0. The other, it could, or 7 minus sigma equals 0, or 3 minus 2 sigma equal to 0. So now if we isolate for sigma in all of these, this one's already isolated, so we have sigma equals 7, and then 3 is equal to 2 sigma, so that means sigma is equal to 3 over 2. So now our values, our possible values for sigma are equal to 0, 3/2, or 7. So every time it pops up in our original matrix, it would be the same number 3 times, and if it were any one of these 3 solutions, it would make the entire matrix non-invertible. All right, that's all for this one. I hope it helps you with your work. I wish you the best of luck and have a great day.